This is a topic on introduction to control system engineering as a general. Then we will move into control system design. What we meant by control system design. The one here is in the robotic lab, the robots in the robotics labs. We have two, this is ABB robot. We also have Puka robot. I'm sure the mechatronics student have, actually there is one lab designed for third year mechatronics student, utilizing these robots. Okay, let's see these two picture. From your opinion, what do they have in common? What are the same between these two common, with two picture, with two incidents? Can you list one or two common thing between these two? Any suggestion from students?
Use wind.
Sorry, wait.
Wind.
Wind. What is this? The first picture, what is this?
Turbulence.
Turbulence or hurricane, something.
Hurricane.
This is an aeroplane. They related to wind. Okay. What else? Wind. Any other thing in common between these two? Both can transport things. No, Izati say both can transport things. Yes, correct. Aeroplane can transport people, can transport cargo, thing from one place to another. Hurricane also. It can bring boats, bring people from one place to another. Of course, we do not want that, but it can happen. So can transport thing or people. Both also very complicated. In control, if we want to model hurricane, it will be very difficult. Of course, people are doing it. People want to predict what happened when it comes, what happened to that is for us to for security, for safety. So people try to predict hurricane. They have to model it. Aeroplane also we do modeling, we do analysis, we also do control. They are but they are, as I mentioned, very complicated. So this maybe, of course, there are many other things in common between these two. They are complicated. They're capable to transport people, goods, and so on. But there is one big difference between these two. One can be controlled, related to this, and the other one cannot be controlled. The hurricane is God created. We cannot control. And so this is the main difference. So if we have a system, in order for us to get benefit from the system, we should be able to control it. If we cannot control, it can be useless, or it can be very harmful to human and to environment. For example, another example is, let's say, power. We have power generated from many places, from solar. We have power, but if we cannot control the one that we obtain, also it cannot be used, or it can be very harmful, very dangerous to human. Okay? So some people say power is nothing without control. Okay? So here I want to mention that power is also important. Not only the system that we develop or generate, then we need to be able to control it, to control that system. And you will see that control is the hidden technology that you meet every day. But because we meet every day, we sometimes do not appreciate the one that we have. Okay, but in actual, power control is used every day in many systems that we use. Control are important, and we have it every day, everywhere in our daily life. The one here is the most basic block diagram. Okay, mind you, the one that I'm discussing is the one that you also have discussed in SKEE3143. Okay. A control system normally shown by a block diagram. Here is a system, and usually we have input and also output. Input and output. The input also is what we call desired response. Desired response meaning the one that we want, how we want the system to behave. That is the desired response. When we excite the system with an input, we get output. The output is actually the actual response. The real one, the real response. And of course, we want actual equal to desire. We want, let's say I want the robot to move 1 meter. So I give input 1 meter. The robot move, and a good robot will stop at 1 meter. That is actual equal to desire. And in that case, error will be 0. But not a good system. Perhaps we want 1 meter, the robot overshoot to 1.2 meter. This is not a good one. Okay? Then in that case, actual not equal to desire. Okay? With an error. Error not 0. This is we do not want it. This is not a good system. So a control system provide output, or sometimes we call response, to an input. Input also called desired response. These are some example of application of control system. This is at PTP, Port of Tanjung Pelepas. There are many cranes. I was informed there are 860 cranes altogether at PTP. The one that we gave to you as the assignment for 3133 is the easiest one, gantry crane, but the one at the port is more complicated. Is actually normally referred to tower crane, something like tower crane. The aim is to move the container as fast as possible. And that determines the performance of the port. And also robotics. In the robotic lab, we have robots. Robot also we need to control. Let's say I want this robot, this ABB robot, to move 60 degrees in order to pick this material. So it have to move 60 degrees. So a good control system will make the arm to move exactly 60 degrees so that it can be able to perform the task. A not good one will be oscillating, maybe some, under dam response, it go to 65 degrees, then oscillate to 55, then it take long time until to get 60 degrees. Some other system not good, we want 60, it moves to 50 degrees. Then we get error, then the robot could not perform the task successfully. So that is, we need control. We need to have an accurate control in order to perform the task. Also, I think in the previous class, some lecturers, they give the elevator or the lift as another example. When we enter a lift, when the door open, when we enter, we normally press the level that we want. Let's say I want to go to level 20. I press 20. The one that we press 20, meaning that we are giving an input of 20, a step input of 20. That means I want to go to level 20. Then the lift from level 0 will start to move. Level 1, level 2, level 10, up to level 20, and stop. This is a very good lift. It can achieve the level that we want. Some not a good one will stop at not exact 20 level 20, maybe a bit different. Some even worse, move to another level. All those involve control system. In industries, the control system are normally categorized into 4. There are many actually. These are the most used. Position control. Position control, I mentioned this one, 60 degrees, that is position control. Okay, robot arm, crane system, elevator, satellite tracking. Many other things involve position control. And usually related to motor, because motor rotate that system. If a big system like elevator that need big motor. Small system, small robot, similar to the one that I showed in the lab, maybe smaller. Crane system, big one, need big motor, high powerful motor. But most of the case related to motor. But of course, besides that, there are many other actuators, such as pneumatic, hydraulic, that also are related to control system. We have speed control, speed of aeroplane. We want to control speed of washing machine, speed of robot, speed of climbing robots, speed of underwater robot, all those related to speed. And normally also the most widely used actuator is a motor, it's an electrical motor. Is an electrical motor. Temperature control. In industry, we want to control in the temperature of that environment. Aircon, when you enter a lecture room, we press 20 degrees Celsius. That means we are giving input. We are giving desired response of 20 degrees Celsius. We want the aircon, the system, to do something, to take action, so that the room will be 20 degrees Celsius. That is temperature control. Besides, in industries, especially in steel industries, they want to have a very hot environment for steel industries, sometime 2000 degrees Celsius. Okay. So that also involves control system to make sure the environment, the chamber is always at 20 or 2000 degrees Celsius. The other one is level control. In industries, especially in process control industries, they normally want to have a standard or a specific level of liquid. The liquid could be acid, could be other things. And also water. We want to make sure the water level at certain height. That is also called level control. So these are four examples of control system application. Of course, there are many other systems, many other controllers designed, developed for industrial application, such as vibration control, to control the oscillation of a car, let's move to this thing, control system configuration. This is very important. The controller can be divided into two. I believe you know this open loop control system. This is the example that we give in the lecture. An open loop system is in which the output is affected directly from the input. That is a one-way straight from input to output. If there are disturbance, in this case, disturbance 1, disturbance 2, the system cannot be modified, cannot be controlled to cater the disturbances. So it is affected only by the input. So we call open loop control system. And the other one is closed loop control system, in which there is a feedback. So this one we call feedback from the output to the input in order to check whether the desired response has been achieved or not. It will be modified based on what we call the error. Error is the difference between input and output. And based on this error, the controller will take action. So here is a controller. We take action so that at the end, the output equal to the input. In this subject, in this course, the one that we will be focusing on is this block diagram. Controller. We want to design a controller so that we achieve the desired response. This is another structure, another diagram showing the differences, showing the difference between open loop and closed loop. This is a motor. This is an open loop controller. Is a straight path from input to output. But if we want to make it as a closed loop system, then we need to take the output, feedback the output by using a sensor. In this case, they use encoder to measure the angle of the motor, and the angle is feedback into the system, and the closed loop controller will take action in order to make sure that the desired response, the actual response equal to the desired response. And this is the differences between open loop and closed loop. I believe you know this. Open loop is simple, it's cheap, but it cannot handle many complicated things, many disturbances. It is limited. In contrast, closed loop is complicated. It will be expensive as we need more sensors, more connections. It will be difficult, and it will be difficult to design. It may involve stability. It may involve in which the system cannot perform as what we want. But in general, they are good. They are less sensitive. They can handle disturbances, and it can also be used to many systems. Okay, let's see specification of control system. Control systems are dynamic. Dynamic meaning that the system is changing with time. Okay, so if I can draw, if I can plot the response, let's say this is the input. This is the input. Let's say we want 1. The input desired response is 1. Then this is the output. It moves from 0, increase to more than 1, oscillate, then it stops. Okay, this is the output. In time, in second. So this is what we call control system are dynamic. That means it is changing with time. 1 second at different point. 2 seconds, different point. If we can say this is a robot moved to 1 second, it moved to maybe 0.1 meter. 2 seconds become 0.3 meter perhaps. So it increased to maybe here at 5 seconds. 5 seconds, it moved to 1 meter. So then it oscillates, and then finally it stops. So dynamic, they are dynamic. Control systems are dynamic. Because of that, there are actually 3 things that we need to discuss related to control system. Because they are dynamic, they're going through what we call 2 phases. The first one is called transient phase. Here, transient phase. Transient means the time to change, changing time. From here, let's say from 0 to 1 meter is transient phase. It takes 5 seconds to reach 1. The second part is called steady state phase. Okay? Steady state means while it stops, when it stops. Let's say it from 0 to 1. When it reaches 1, stop at 1, then that is steady state phase. And the response here we call transient response. Transient response. And here is called steady state response. So in order to describe system, let's say the robot, in order to describe the robot, whether the robot is good or not, we will describe by looking into the transient phase or transient response, and also looking into the steady state response. And the other one that we want to look also is what we call stability. You did stability, you check stability using Rose-Lewis criteria. We also want to check stability. Is the robot stable? If the robot not stable, we will have a case like this. It starts from 0, increase to is okay, but finally it increase without stopping. We want it stop at 1, but it keep moving up to other point. So of course it will be very dangerous to human. It will be very dangerous to environment because of instability. So this is called unstable system. We want a stable system. A stable system will have steady state response. Okay, so steady state response only applicable for a stable system. Only a stable system will have steady state response. Because unstable, it moves, it cannot stop. It's still always on transient. This is the specification of control system. And also mentioned here in the slide, the same. Here we take the elevator as the example, transient response and steady state response. And another thing that we learned last time is steady state error. Steady state error is the difference between input and output. We want error, zero steady state error. We want output equal to the input. Based on the specification, the one that we showed just now, we discussed just now, this is the control system objective. It's common to all systems. It is the objective. There are three objectives of control system. When we relate to system response. First, we want a satisfactory transient response. If this is the transient response, we want a fast system. We want fast rise time. We want fast settling time. We want, if possible, zero overshoot, no overshoot. Then system like this is good. Good system, no overshoot. It goes straight to the desired point or desired rotation or desired temperature. No overshoot. So this is one of the objectives. Second one, we want a stable system. Of course, this is important. As I mentioned, if the system not stable, then there will be no steady state response, no steady state error. System will be very difficult to control. And the last one, our objective is to have zero steady state error. That means the output equal to input. These are three objectives. If you learn during undergraduate, if you would like to further study on control in master studies, or you want to focus on control during PhD, but all these are the same. These are the objectives. People are discussing this. PhD students also are discussing the same objective. They want to develop control, a good controller, in order to achieve this objective. Of course, they apply to many other more complicated systems. But still, the objective remains the same. We want a satisfactory transient response We want a stable system. We want zero steady state error. Okay. For all systems, any system, at any level. Okay, then we move into design step. How can we design a good control system? What step that people are using? First is model. Let's say I have a robot or any system, I have power system. I have electronic circuit. Okay, all the same. First, we will start by doing what we call modeling. We need to model the system. This is what we focus in the previous lecture, previous course. We do modeling of dynamic system. What we will get by doing modeling? We get differential equation. Remember, electrical circuit, RLC. You did model, you model it, you use Cramer's rule, but finally you get differential equation. That is the outcome of modeling. A mathematical model, a mathematical equation representing the model. Once we get differential equation, we can also represent in a transfer function. In chapter 2, in 3133, focuses on transfer function. Any system with electrical, motor, mechanical system, rotational system, all those, finally, what we want is a transfer function. And also, it can also be represented in a state space approach. Remember, we have x dot ax plus bu, y equal to cx plus du. This is a state space model with 4 matrices A, B, C, D. So that is the first step. When we want to control, we know the system, we study the system, we model the system. Of course, there are many techniques to model. Once we have obtained the differential equation or transfer function or state space, then we can do simulation. Now we want to analyze. We can simulate. Simulation using CACSD, meaning computer aided control system design. One of those, of course, one of the most popular one, of course, MATLAB. You can also use Scilab. It's free. It's an open source. You can use LabVIEW. You can use many other languages, many other programs, computer programming, that can simulate the system. Once we obtain the differential equation, once we completed the modeling. So we do simulation, then we analyze. Based on the mathematics, we analyze whether the system is stable, where are the poles, how it look like, is there error, what is the rise time, settling time, all those we call analysis in time domain. Okay, and actually there is another domain called frequency domain. Frequency domain will be covered in this course. Once we analyze, we know the system performance, then next is to design a controller in order to achieve the desired response. If without controller we can achieve, then no need to do control. If the system is already good, then use that one. But if that system that we design is not capable, is not able to obtain our desired response, then we need to design a controller. There are many controllers. As I mentioned just now, PID, lead lag, state feedback, optimal control, robust control, adaptive control, intelligent control, many other controllers. Of course, we cannot cover all. And once we design a good system, a good controller, then we can proceed to develop the prototype, to develop or to design the actual system and implement the controller that we have designed. To show where we are, the first three parts until here is covered in system modeling and analysis. We do modeling, we show you how to do simulation, especially by using MATLAB for the current project, and analysis. We show you what is the purpose of pole, zero, finding the transient response, the time, the error, the stability, all those is analysis. The one that underlined in red is the one that will be covered in this subject, control system design. Of course, there are many controllers, but we, for this, for introduction to the student, we will show PID, which is in time domain, and also lead lag in frequency domain. And before that, we will also show and discuss bot plot in frequency domain and root locus in time domain. So this is the one that we will cover, and the relationship between the previous subject and this subject. As I mentioned, we also have 4133 modern control system. Modern control system will be mainly related to state space. We have done state space in 3133. We managed to get the model. Then modern control system is the analysis and the controller design based on the state space model. For example, state feedback. State feedback is related to, because we call state, also state here, state variable. State feedback, it will be discussed in modern control system. In another way to show you the design step, let's take a crane. This is a crane available in the lab, a small scale crane, 1 meter by 1 meter crane. It can move in X direction, in Y direction, and also in Z direction, meaning that the length can be changed. So it's a 3D crane. Let's say we want to control this crane. First, we need to model the crane. You did it in the project, in the previous project, you model the crane. Okay. Of course, a 3D crane will be more difficult because it involves more parameters. You have to consider the simultaneous effect, simultaneous movement of in X and Y. So more difficult. The formulation is more complicated. But still, the aim is to find the differential equation, to find the transfer function, and finally the state space model of the crane. Once we get the model, once we get the equation, we can use simulation, we can use Simulink, we can use MATLAB, we can use LabVIEW in order to analyze the system. Okay? Based on the model that we obtain, we do simulation, then we get the result, and we can analyze. This is the uncontrolled system response, the system without controller. We can analyze whether the system is good, or the system is bad, or the system is satisfactory, no need to control, or we need a little bit control, or some variable need to be controlled, the other one no need to be controlled. So that is based on the analysis. And that analysis, of course, based on modeling, the model that we get, and then we simulate. This is the one that we covered in 3133. In 3143, we will focus on controller design. Assuming that the system is not satisfactory, the performance of the system is not satisfactory, we need to improve the system, we need to make it faster, we need to, because the oscillation of the load is high, we want to reduce the oscillation, then we need to do or to design a good controller. For example, we want to design a closed loop controller. Again, when we design, we will get an equation, also mathematics. We get the equation, then we can again do simulation use with the controller. Okay? We can simulate, we can change the parameter of the controller, we can change the gain, we see what happens if we use different gain. We want to find the best gain that gives the best performance of the system. Then we study. Perhaps now you see, I took this example. This is actually from the real crane. I take example the plot of the real crane in X. It moved to 1 as what we desire, from 0 to 1. Okay. Then once we satisfy with that, we will implement on the real crane. Okay, so this is covered in 3143 until here. Of course, we will not be able to implement on the real system. This is an example of crane. Many other systems, of course, we were not able to continue with the experiment on the real system, but at least we will do until here. Okay, from controller design until we analyze whether the system, the controller that we design, obtain the desired response.